How's it going, everyone? There was a good question asked in one of my classes recently, and I wanted to make a video on that. The question was, can you prove the Earth is round without going to space or sailing around the Earth? Okay, and the answer is you definitely can. You can demonstrate that. And people knew that the Earth was round before we could fly to space and before we could sail around the Earth. So the easiest way that you can demonstrate to yourself that the Earth is round is just go to somewhere with a large body of water, a large sea, a sea, an ocean, a large lake, and look at the horizon. Look at that watery horizon. It's actually a curved line, and you can see it with the naked eye. Okay, it's a very subtle curve, more subtle than what I just drew, but the horizon is curved. You can just see it. If you pay attention, you'll see it. Okay. In general, the existence of a horizon, unless you're looking at uphill, the existence of a horizon is also a sign of the curvature of the Earth, right? That there is a line beyond which you can only see the sky, right? But that line moves away from you as you get closer to it, right? That can only happen on a curved surface, right? Where there's a certain point beyond which your vision, right? Your line of vision can only see the sky, right? And the land ends. If the Earth was flat, there would be no horizon, right? And you look at a body of water, as you look farther and farther away, you would not see only the sky. You would continue to see the Earth. It would just get very, very blurry that you wouldn't be able to make it out. And this effect of the horizon is actually one of the things that in ancient times hinted to people that the Earth is in fact round, other than paying attention and seeing that the horizon is actually curved. People would see a ship sailing away, right? And as they see it sailing away, okay, so first there's the water, and there's your ship in the water. Okay, we've got a rear view of this ship. And then as the ship gets farther away, eventually it looks like this. And as it gets even farther away, it appears to dip into the water. Okay, you start to see something like that. And then eventually you just see that sail sticking up, and eventually you can only see the top of the ship, and later on, well, that whole ship is just not there. And if you use a telescope to get a closer look at the ship, that ship will not rise out of the water. Okay, the part of the ship that has gone beyond the horizon will still not be visible if you use a telescope. And why that's happening is, again, because that ship has sailed beyond the curvature of the Earth, right? So if you're an observer looking right here, right, your line of sight is limited, right, by the curvature of the Earth. So what you would see in this situation is you would just see where the sail is. You would not see the base of the ship because it is beyond the horizon. It has traveled past the curvature of the Earth. And a telescope will allow you to see that sail bigger, but it will not allow you to see the actual hull, the actual base of the ship. Okay? So that is another experiment that you can do. If you can't see a ship sailing away where you live, you can also do this with islands. Okay, there could be land and water where you live, and there could be an island. Let me draw that for you here. Okay, so there's the curved Earth, and there's a shore, and let's say there's a building. Okay, and if there's an island right here, okay, if you're an observer standing on the coastline, you may only see that tree sticking out of the water. right? It would look something like that. But if you were to stand on the roof of the building or looking from the window of a building, you would actually be able to see part of the island's land. Okay, so that is another way to see the curvature of the Earth. Something else you can do, if you have a friend that lives in a different enough time zone that it is dark over there when it is bright where you are, or vice versa, it's bright where they are when it's dark where you are, just call them up, tell them to turn on their video, and they'll show you in real time how it's dark where they are when you're seeing the sun, or vice versa, which tells you that there's two sides of the Earth. Okay, when the sun is hitting one side, it's not hitting the other side. Now, in ancient times, people didn't have that kind of communication technology, but there were other experiments that could be done. For example, how shadows fall in different parts of the Earth. If you have a flat surface and two wells, for example, that are far enough apart, and you have a source of light, well, how that light is going to fall in one well is different than how that light will fall in a farther away well. Okay, but if the surface was curved, okay, then there is a difference. There would be a difference between the flat situation and the curved situation. Okay, notice that in the first well, when we have curvature, the light gets deeper in there. In the second well, when we have curvature, the light does not get as deep in there. So two friends, say one in Greece and one in Egypt, in ancient times, can agree that, okay, on this day we're going to record how the light from the sun travels along the wall of a well nearby. And then they can compare notes and see, okay, you know what, this looks like the Earth is curved, and more than that, they can actually calculate what that curvature is. Now, if we're going to be honest scientists about this, we also have to ask the opposite question. Are there experiments one can do that will demonstrate that the Earth is flat? And the answer, brace yourself, is yes. Here's a simple one. Take a flat object, like turn a table upside down, or take a large flat wooden board, or take a large piece of cardboard, and just put it on the ground. And you'll see that it sits sturdily. It does not roll or anything. It sits as if it is sitting on a flat surface. There's a more complex experiment you can do. Take 3 points in your town. Okay, they could be 3 trees or 3 buildings, and make a triangle. Make a triangle. Draw a triangle with chalk or string, or just imagine where the lines of that triangle would go, and look at the angles of that triangle. Okay, look at the angles of that triangle and add them up. And if they add up to 180 degrees, guess what? You're dealing with a flat surface, because the 3 angles of a triangle will add up to 180 degrees on a flat surface. You could also make a right angle triangle. Easier to do with buildings than with trees, just because of the way cities are built. Right? Create a right angle triangle. Okay, 3 buildings that form a right angle triangle, and see if the Pythagorean theorem holds. Okay, if you square one side of the triangle and add it to the square of the other side of the triangle, will you get the square of the hypotenuse? And if the Pythagorean theorem holds, guess what? You're dealing with a flat surface, because the Pythagorean theorem holds specifically on a flat surface. So, how do we reconcile these two phenomena? On one hand, we can conduct experiments that demonstrate the Earth is round. On the other hand, we can conduct experiments demonstrating that the Earth is flat. So if we do not actually sail around the Earth or go to space and see what's going on, well, here's how we reconcile them. These experiments showing that the Earth is flat they only work in a small area. Okay, if your town is small enough, if these buildings, if these trees are close enough together, not too far apart, well then the Pythagorean theorem will hold. The angles of your triangle will add up to 180. If your flat, large object, like a wooden board or an upside-down table, is not too huge, it will sit flat on the earth. But once you're talking about 3 points forming a triangle that are far apart, like 3 different cities, or even 3 different buildings in a large enough city, well then you'll see that the earth is round. Then, if you're measuring accurately enough, the Pythagorean theorem will not hold. And the angles of that triangle will not add up to 180. And if you have a large enough flat object, for example, a highway, a road, that's straight enough that you could see along it, you will see that it does not lay flat. It does go over the horizon. And if you're living in a place where there's a far enough straight road, you can see cars and bridges disappear over the horizon in the same way that you see a ship disappearing over the curvature of the earth, over the horizon, as it gets farther away. Okay, it can happen, right, with cars and bridges too. Okay, where as it gets far enough, you only see the top of it, and then eventually you don't see any of it at all. So, what does that tell us? That on a small scale, the earth is flat, and on a large scale, the earth is round. And because our measurements are limited to the accuracy of our measurement equipment, what it really tells us is that on a small scale, the earth is approximately flat, and on a large scale, it is approximately round. And that's true. That's true, and how that can be true is if the earth is round but also really, really big. Okay? When something is round but also really, really big, well, if you take a small section of it, it's so close to flat that it's pretty much flat, and you can treat it as flat, and your measurements will be close enough that they will agree with a flat surface. But when you pick a large enough region, well then the curvature is substantial enough that you can no longer treat it as flat. And that's that. So not only can you demonstrate that the earth is round without going to space or sailing around it, you can even measure its curvature, and on a small enough surface you can measure you can make measurements using the flat approximation on a small surface. And by the way, looking over the horizon at a body of water, seeing the curvature of the earth, if you're on an airplane, you can see that curvature even more easily. Now, of course, then you have to go on an airplane, which was also not possible in ancient times, but check it out, look at the window next time you're on an airplane as well. So, I hope that was informative, and until next time, enjoy.